Today we're going to go over optimization. And optimization is the idea of maximizing or minimizing a quantity. And since we have done some work with first derivatives already, we know that your first derivative is used to find local maxima and minima. And then if you are also given a particular interval to look on, you can find the absolute maxima and minima. So optimization takes that strategy or that skill with first derivatives and applies it to actual contextual situations. So optimization problems require to find the maximum or minimum of a quantity. The optimization problems are not necessarily the same as far as what information you're presented with. So they do require some careful reading to identify what we are given and then what we're trying to find. And I have come up with some very general guidelines and kind of steps you want to take when solving optimization problems. So these steps are draw a picture if possible. So for example, you'll see in our first problem that we do together, a picture won't actually be necessary, but I usually like to draw one because it helps me assign variables to my unknown quantities. And so those two kind of go hand in hand. Step 3 is we want to determine what equation we want to optimize. So sometimes you want to find like the maximum area or the minimum volume or the minimum cost of producing something. So there will be an equation that we write for what we want to optimize. Then we have to determine the constraints, which means that, for example, you can't have, if I'm measuring the length of fencing that's going to go around a field, you can't have negative fencing. So one of my constraints would be that your lengths would have to be positive no matter what. Or I might have a limited amount of material to build something out of, and so that material might put a constraint on how voluminous that thing can become. So that would be a constraint equation. And what we do is we use that constraint equation to write our optimization equation with just one variable. So at the end, before we try to optimize an equation, we want it to like only have x's in it or only have y's. We don't want to be doing any implicit differentiation here. Then you're going to take the derivative, differentiate the optimization equation, and use your first derivative test to determine relative extrema. And then, of course, our relative extrema, as we know, could be the very maximum and very minimum, or we have to look at our endpoints as well. And then once you're done with that, you actually want to go back and answer the freaking question, AFQ. So you want to apply any of your constraints or your original equation to determine your final answer. If they want the maximum area, your final answer better be the maximum area, not just what dimensions would make that happen. So I figured we'd go through a couple of examples and then we could do a couple more together later. So let's look at this first example. So in example 1, it says find two positive numbers where the sum of the first and twice the second is 100 and the product is a maximum. So first we need to identify, or I'm not going to draw a picture for this because I don't know how to draw a picture for numbers. I'm just going to assign some variables to the numbers. So I want to find two positive numbers. So I'm going to call one of those positive numbers x, and I'm going to call the other one y. I know, really original. And then, so I have my variables. Then I want to figure out what I'm trying to maximize or minimize. And in this scenario, I'm trying to maximize the product of these two numbers. So I want to maximize the product, I'm going to call it P, of two numbers. And so what's the product? It's when you multiply them together. So x times y. So this is the equation I want to maximize. And then let's talk about the different constraints that happen. First and foremost, our constraints have to be that these are two positive numbers, so I know that x is greater than 0 and y is greater than 0, so those are going to be some constraints. And then I also am given some more information of the problem. It says where the sum of the first and twice the second number is 100. That's just another constraint that this problem is putting on my numbers. So the sum of the first, so this is my first number, and twice the second equals 100. So I know that when I add my first number and twice the second number, I get 100. Okay, so I have my variables, the equation I'm trying to maximize, my constraint equations, and now I'm going to use my constraint equations to rewrite this so it only has x's in it or only has y's in it. So I'm going to go ahead and let's see if I solve this this is more easily solved for x. So I have another way to write this constraint equation is x equals 100 minus 2y. And so now I can combine that. I'm going to take that piece and I'm going to plug it in for x right here. So then I can rewrite my equation I'm trying to maximize. So I guess we should kind of do some step numbers here. This would be step 3, I believe, is always to write the equation you're trying to maximize. And then step 4 is to write your constraint equations and then use them to write our maximize our product in one variable. So I'm replacing that x with 100 minus 2y. And then there's still that y there. Okay. I'll go ahead and simplify a little bit. So 100y minus 2y squared. Okay, and now I'm going to, since I have an equation that it has only one variable in it, I can take the derivative of that. So step 5 is going to be to find p prime, which will just be 100 minus 4y. And then now I'm going to basically apply the first derivative test to this. So I'm going to set it equal to 0. So 0 equals 100 minus 4y. And then if I solve that for y, I'd end up with what? Y equals 25. Okay, so this is what my critical number. And then I'm going to want to make sure to plot it on a sign chart just to make sure it is indeed a maximum. So if I plug 25 on there, apply my first derivative test. So if I plug in a number less than 25, like 1, I get a positive number. And if I plug in a number bigger than 25, I get a negative number. So, yep, this is a maximum. And so my y equals 25 is going to be one of the numbers that when I find the product of x and y, I end up with a maximum product. In this scenario, I don't really have endpoints I can be testing because it just says that x is greater than 0 and y is greater than 0. So it's not like they tell me that my x values have to be between a certain number and my y values have to be between a certain two numbers. So y equals 25 will help produce a maximum product, but I want to find the other number too. I want to find both positive numbers where the sum of the first to my second is 100 and the product is a maximum. So I have one of my numbers, I have the second number, so y equals 25. To find the first number, I just have to plug it back into this equation, so into my constraint equation. So x equals 100 minus 2 times 25 would equal 50. So my answers, my final answers, are x equals 50 and y equals 25. These would be two positive numbers that meet my constraints but result in a maximum product. Awesome. If you want to put this purple part right here, this was step 6. Beautiful. And then I sent in our variables. That was step 1/2. There you go. All right, let's go ahead to another example. All right, so in this example, a farmer plans to fence a rectangular pasture adjacent to a river. The pasture must contain 180,000 square meters in order to provide enough grass for the herd. What dimensions would require the least amount of fencing if no fencing is needed along the river? So I'm going to draw a picture for this one. So I have a farmer who's got fence, fence, fence. Oh, and then along here is a river. So you don't actually need any fence around there. There. Some waves in the river. Or birds. Depends on your view of it. Okay, so then I have my picture. My variables, this is a rectangular pasture, would be, let's see, x on this side, x on this side, and then this one would be y because it's a rectangle. So that's, I guess, step 1 and step 2. And then what we want to do now is figure out what we're trying to maximize or minimize. So I'm trying to, what dimensions would require the least amount of fencing if no fencing is needed along the river? So we're trying to minimize basically the perimeter. So I'm going to call it P again. And then my perimeter would be the equation 2x plus y. This fence plus this fence plus this fence. This is what I'm trying to minimize. Step 4 is to write out our constraints. So again, I think x and y both have to be positive because you can't have negative fencing. But then we also have some more information that our pasture must contain 180,000 square meters in order to provide enough grass for the herd. So the area has to be 180,000 square meters. So 180,000 has to equal area, and area of this would be x times y. So this is my constraint equation. Now I can go ahead and I can solve this for either x or y. I think I'm going to go ahead and solve this one for y. So I'm going to divide both sides by x. It doesn't technically matter. You can do it either way. So then I end up with the equation y equals 180,000 x, which means that I'm going to take this and I'm going to plug it in here so that I can rewrite the equation I'm trying to minimize in one variable, or with one variable. So here's I'm going to move it up here. So P will now equal 2x plus 180,000 over x. And then now I'm going to go ahead and step 5 is to take the derivative and then, apply your first derivative test. So P prime would equal 2, let's see about this. Another way we could have written that would have been as 180,000 x to the negative 1. So the derivative of that would be negative that x to the negative 2. So the derivative of that would be, not positive, negative 180,000 over x squared. Lovely. And so then I'm going to start doing my first derivative test, set it equal to 0. Move this over so it becomes positive. So 180,000 x squared equals 2. And I'm going to run out of room. All right, so then multiply by x squared on both sides. So 180,000 equals 2x squared. Divide both sides by 2. Awesome. So I'm just going to make a little, we're going to do it over here. So then we have, let's see, x squared equals 180,000 divided by 2, which is 90,000. And I believe if I square root that, I get 300. Awesome. I know it can't be positive and negative 300 because our x value has to be greater than 0. And then you would want to do a sign chart test here just to make sure it's a minimum. So let's see if I've got 300 and I do my first derivative test. So if I plug, where's my first derivative over here? If I plug in like the number 1, for example, 2 minus 180,000 would definitely be a negative number. And if I plug in the number like 19 billion, this fraction would get really small. So 2 minus a very small fraction would still be a positive number. So yes, in fact, it is a minimum. And then again, I don't really have endpoints here to test because it's just x has to be positive. So my last thing I'm going to do is I'm going to find if x is 300, I need to find my y value. So I'm going to use this constraint equation again, kind of like what we did up here. So I'm going to find my y value. Oh, that's not what I started last time. Plug this in to right here. Yep. So y equals, just trying to stay consistent, 180,000 divided by 300 squared. So 180,000. Oh, not squared, not squared. Just 300. Would give me 600. So then my final answer would be what dimensions would require the least amount of fencing? So you would need a 300 by 600, yeah, rectangle. So a 300 meter by 600 meter rectangle. Awesome.